All right, welcome everybody. So in this video, we are going to define what an orthogonal set of vectors are, and then we'll see why such sets are going to be really nice. In this video, we'll see that such sets of vectors are actually going to form a basis. So let's consider a set of p vectors v1, v2, all the way up to vp, and these are all vectors that are in Rn. So such a set of vectors is said to be orthogonal set if the dot product of vi and vj is equal to 0 for I not equal to j. So in other words, taking any pair of vectors, their dot product gives us 0. So every vector in the set is orthogonal to every other vector in the set excluding itself. So let's take a look at an example. So let's imagine this set of three vectors. The first vector is a dimension 3 column vector, 1, minus 1, 0. The second vector is 1, 1, 0. And the third vector is 0, 0, 1. So is this an orthogonal set? Well, then that means we would need to check to see whether v1 dotted with v2, does that give us the scalar 0? And so here we can check that we would get 1 minus 1 plus 0. So yeah, that one does check out indeed. And then we can go and take a look at v1 and v3. And what do we get when we take the dot product of those two vectors? I would get 1 times 0 plus minus 1 times 0 plus 0 times 1. So we get 0 plus 0 plus 0, and that gives us 0. And then we have a third pair that we need to check, namely what happens if I take the dot product of v2 and v3, and here we can check that this dot product is also 0, since I get 0 plus 0 plus 0. So all three of these dot products give us 0, so that means for any pair of vectors in this set, the dot products are all equal to 0, so this would indeed be an example of an orthogonal set of vectors. Okay, so now that we've defined what an orthogonal set of vectors are, let's take a look at why such a set of vectors is particularly nice. So let's consider the following theorem, that if S is a set of p vectors v1, v2 up to vp, if this set S is an orthogonal set of non-zero vectors, we're going to assume that all of these vectors in the set are not zero vectors, then as long as S is an orthogonal set of non-zero vectors in Rn, then it will follow that S is linearly independent set, and therefore S is going to, this set of vectors forms a basis for the subspace spanned by S, since they're a set of linearly independent vectors that span the entire subspace. So that would make them a basis for the subspace spanned by S. So let's take a look at the proof of this theorem. So let's prove this by contradiction. So we're going to suppose that S is an orthogonal set and the opposite of what we're trying to show, and that the vectors in S are linearly dependent, and we'll show that by assuming this, we're going to reach a contradiction, so that our assumption must be incorrect, and therefore the opposite is true, that S is going to have to be linearly independent. But let's first assume S is orthogonal and the vectors in S are linearly dependent. So that means there exist scalars c1, c2 up to cp, where at least one of these scalars is non-zero, such that taking a linear combination of the vectors in set S, we get the 0 vector back. And so by assuming these vectors are linearly dependent, that means there exist such scalars that when we take linear combinations of these vectors in set S, we can get the 0 vector back. So now let's consider the following, that if we take the 0 vector inner product with v1, right, we're going to get the scalar 0 back, since we're going to be multiplying every entry in the vector v1 by 0. And now let's replace the 0 vector with what we have assumed that there exists some linear combination of these vectors in set S that give us the 0 vector back. So I'm going to replace the 0 vector with C1 V1 plus C2 V2 plus CP VP. We're going to take the dot product with V1. So we can use properties of the inner product to pull out each of these these scalars, and distribute V1 through each of these terms. So the dot product in the line above can be rewritten as C1 times V1 inner product with V1 plus C2 times V2 inner product with V1 plus all the way up, and we've got a missing plus sign right here, all the way up to CP times VP inner product with V1. And since we've assumed that S is an orthogonal set, this tells me all of these dot products where I take V1 and take the inner product with another vector other than V1, these are all 0. So the only term that's going to be left after calculating all of these dot products is this very first one. And now recall that we have assumed that all of the vectors in our set S are non-zero, that the only way I'm going to get C1 times the V1 dotted with itself equals to 0 is either V1 could be the 0 vector, in which case V1 dotted with V1 would be the 0 vector, but that can't happen because all of these vectors are non-zero. So the only way this product gives us 0 is if this scalar C1 is equal to 0. And if we repeat this calculation, this process, we can similarly show that all of these other constants, scalar multiples, C2, C3, all the way up to CP, they all have to be equal to 0. And the way that you would show that is we put V2 over here, we put a V2 over here, and then going through the same process, you would get to the point where C2 times V2 dotted with itself gives us 0, and that's going to therefore imply that C2 is equal to 0. And then we do this again with V3 and so on. So repeating this several times over, we can show that C1 is 0, C2 is 0, and in fact, all of these constants have to equal 0. But that contradicts our original assumption that these vectors are linearly dependent. So that can't be the case, and the opposite must be true, namely that S is linearly independent. All of the vectors in S are linearly independent, so S is a linearly independent set, and therefore it's going to be a basis for the space spanned by S. And so this theorem shows us one reason why orthogonal sets are particularly nice, that orthogonal sets by default for our linearly independent set, and they give us a nice way of generating bases.